Welcome to the video series, The Operational Amplifier, From Abstraction to Reality. This is part 2 of an attempt to get an understanding of the specifications on an op-amp datasheet. At this juncture, we transition from abstraction to reality. Let's begin talking about open-loop voltage gain. Here's an excerpt from the TL07 series op-amps. It shows a typical gain of 125 dB. That's 1.7 million. Here are the test conditions. The voltage supply is 40 volts. The common mode voltage is centered at half the supply voltage. The load resistance is 10K. And the output voltage is within 0.3 of a volt within the rails. The main takeaway is this is only at DC or near DC. Remember when we took a peek inside the op-amp, it contained a compensating capacitor, which was a Miller-connected capacitor. This gives the op-amp a single-pole, low-pass response. It's made that way to ensure stability at unity gain. Here's what the response looks like. Since it's a single pole, it rolls off at the rate of 20 dB per decade. Here's the control theory model of an op-amp we introduced in the history of the op-amp video, introducing the concept of negative feedback. Let's review that. A sub V is the open loop gain of the amplifier, the gain without feedback. Ideally, this gain would be infinite. We want to determine the closed loop gain of the negative feedback system, which is the ratio of the output voltage V sub O to the input voltage V sub I. It's the gain with the negative feedback loop closed. The block labeled beta is the feedback factor. In our current example, this is a set of resistors performing voltage division that programs the gain of the amplifier. Beta times V sub O is the portion of the output fed back to the input. A sub V times beta is the gain around the feedback loop. Let's write the loop equation for the output voltage. It's A sub V times the input voltage minus the product of beta times the output voltage per the diagram. This equation is rearranged to show the ratio of the output voltage to the input voltage, which is the closed loop gain. In our sense of abstraction, we made the assumption that the open loop gain is near infinity. The term 1 over A sub V becomes 0, and the closed loop gain is simply 1 over beta. Now that reality is set in, we need to back up. We must consider the effect of the open loop gain to not be infinite, but be finite gain at some frequency. That 20 dB per decade high frequency roll-off will impact the closed loop gain performance. Let's say we want to operate at a frequency of 100 kHz. With the open loop gain shape, we only get 40 dB of gain at that frequency, which is a voltage gain of 100. In this example, we desire a gain of 51 or 34.15 dB. The feedback factor, beta, is the reciprocal of the closed loop gain and is 0.019. RF is 500 ohms and R1 is 10 ohms. The actual closed loop gain is a disappointing 33.77. That's only 66% of our desired gain of 51. By the way, this closed loop gain equation we derived from the control loop math only applies to the non-inverting configuration. Let's go ahead and derive a closed loop equation for the inverting amplifier in terms of beta being the same as for the non-inverting configuration, R1 over R1 plus RF. The voltage at the inverting input can be written as a simple voltage divider between Vout and Vin. With the non-inverting input grounded, Vout is just the open loop gain, AV times VA. We need to eliminate VA, which we can do by substituting V out over minus AV in its place. Now we just need to rearrange the equation in terms of V out over V in, the closed loop gain. Here's the equation to calculate the closed loop gain with a known finite open loop gain on an inverting op-amp. This seems a bit onerous, doesn't it? There's a better way to determine if your op-amp's open loop bandwidth is good enough for your desired gain. At some point, somebody decided it would be a good idea to multiply the gain of an op-amp by its bandwidth and call it the gain bandwidth product. It's a genius move. It's a very accurate approximation, especially after you get past the frequency cutoff of the compensation pole frequency. Here, with a gain of 120 dB, or 1 million volts per volt, the gain bandwidth is 1,000,000 times 10 hertz is 10 megahertz. Let's say we want to operate with a closed loop gain of 40 dB, or 100 volts per volt. 100 times 100 kilohertz is also 10 megahertz. Since the open loop gain varies widely, there's a more definitive approach to specifying the gain bandwidth product. It's specified at unity gain, or 0 dB, which is also 10 megahertz. Here's the datasheet for the TL07 series op-amp. It has a specified gain bandwidth product of 5.25 megahertz. If you are so inclined to plot the open loop response as a function of frequency, like I have, it's real easy. You just use the simple single pole transfer function using the DC open loop gain and cutoff frequency. Since the gain bandwidth product of the TL07 series is 5.25 megahertz, just divide it by the gain of 120 dB, which is 1 million volts per volt, which gives us 5.25 hertz. That's the 3 dB cutoff frequency. In this case, the single pole plot uses a gain of 1 million and a cutoff frequency of 5.25 hertz. If you want to plot the closed loop gain, let's say 10 dB, divide the gain bandwidth by the voltage gain of 10 dB, which is 3.16 volts per volt, which yields 1.66 megahertz. Then use the 1.66 megahertz as the cutoff frequency and the gain of 3.16. It's probably not always necessary to plot the gain curves, but I think this exercise helps to make the subject have more clarity. If we needed an amplifier with a voltage gain of 10 dB, by using the gain bandwidth product, we know right away the usable bandwidth of the TL07 series op-amp is 1.66 megahertz. The next spec to discuss is the large signal differential voltage amplification parameter. The distinction here, as the name implies, is regard to a large signal. The test conditions for the TL07 series include a VO of plus and minus 10 volts with a 2K load resistance. The specified minimum large signal differential voltage amplification at room temperature is 25 volts per millivolt. That's only an amplification of 87 dB, which is way below the DC open loop gain above. The DC value of the large signal differential voltage amplification is published in the datasheet tables, but large signal differential voltage amplification is frequency dependent. Here's the response of the TL07 series over frequency. This is a design issue when precision gain is required. Consider the equation for real open loop gain here when assessing the impact of gain precision versus actual large signal gain at a specific frequency. I made a test circuit to measure the large signal response of a TL07 series op-amp. I used 100 Hz and 10 kHz sinusoidal inputs separately. I capacitively coupled the input to overcome any DC bias the signal generator may have. I measured the input at TP1 and divided down the signal for better amplitude control with the signal generator's vernier. I set the gain for the device under test to 1001, I adjusted the input amplitude in each case to have a 20-volt peak-to-peak output at TP2, consistent with the datasheet's plus and minus 10-volt output parameter. Here are the measurements at about 10 kHz and another set at 100 Hz. I rearranged the closed-loop gain equation to solve for AV, the open-loop gain. I put the measurements in a spreadsheet and calculated the effective open-loop gain. As you can see, the gain is fairly good at 100 Hz, but is very low at 10 kHz. Let's see how this compares to the chart in the spec. The gain of 18,589 at 100 Hz is just below the line. The gain of 268 at 10 kHz is right on the line. The main takeaway is the reality that an op-amp may not have enough large signal capability to attain precise gain. Always calculate the closed-loop gain using the large signal amplification at the highest frequency of use. In many cases, where high gain and large signal is required, a set of cascaded amplifiers are necessary. Next up is the input parasitic elements. Both inputs of the op-amp have parasitic impedances, both differential and single-ended. The inductance is not specified and is negligible at the frequencies that op-amps operate on. Input impedance is a design issue when the source impedance is high. Perhaps most important is the input capacitance will cause extra phase shift in the loop and will erode phase margin. The input capacitance is measured between the input terminals and either input grounded. If you ground VP, the input capacitance is CD in parallel with CN. The common mode capacitance is measured with VP shorted to VN and is CP in parallel with CN. In other words, the capacitance of the common mode source would C to ground. Input resistance is the resistance between the input terminals with either input grounded. The differential input resistance is the small signal resistance between the two ungrounded terminals. Usually, the input impedance is specified as a parallel combination of input resistance and input capacitance. Here's the datasheet for the microchip MCP601. Being a CMOS op-amp, the input resistance is a stunning 10 teraohms. That certainly supports the ideal op-amp abstraction. Moving on now to output impedance. Here again is a simplified op-amp schematic with an emitter-follower push-pull output. With the op-amp having negative feedback, the output impedance is theoretically zero because the emitter of Q6 will go as high as it needs to go to close the loop and overcome the drop across R1. This is true up to the point where you run out of headroom. The output impedance of an op-amp is specified as the open loop output impedance. The actual closed loop output impedance depends on the open loop gain and the feedback factor. This is the typical voltage-controlled voltage source op-amp model with a feedback loop and a load resistor. This is the equation for the closed loop gain found in textbooks designated as RO prime. To help me understand it better, I felt the need to derive it. Maybe it will be insightful for you as well. We will start by grounding the non-inverting input terminal. Also note, the output load resistance will include the feedback loop components as well. Using KVL, we can write a loop equation through the op-amp and rearrange to solve for output current. The differential input voltage is Vn minus Va, and since Vn is 0, Vd equals minus Va. And then substitute Va in place of Vd. The feedback factor beta is Va over Vo, and we can replace Va with beta Vo and factor out Vo. We then write RO prime as Vo over Io. The Vos cancel, and we get the expression for the closed loop output impedance. It's apparent to see as gain A tends toward infinity, the closed-loop output impedance goes to 0. But in the real world, it's not always the case. Here's the open-loop output impedance for a TL08 series op-amp. At 1 MHz, it's 125 ohms. But check out the open-loop gain at 1 MHz. It's only 15 dB. Let's calculate the closed-loop impedance. For a beta of 1 and the 15 dB closed-loop gain, we get 18.9 ohms. But let's say we had a program gain of 101, which is beta of 0.01. We would get nearly all the open-loop resistance. Not only that, but the open-loop gain of only 15 dB would not give us a gain of 100. This is more of the reality of op-amps where the ideal op-amp abstraction does not hold. With a resistive load, the effective output impedance is simply a voltage divider reduction in output swing capability. But a capacitive load can cause a stability problem. The output voltage as a function of frequency is a single-pole low-pass function with the magnitude here. The cutoff frequency is when the reactance of the load equals the output resistance. That TL08 series had an open-loop output impedance of 125 ohms. If the open-loop gain in beta resulted in most of that being the closed-loop impedance, it wouldn't take much of a capacitive load to erode phase margin. Let's look at an example. At 1 MHz, the load capacitance of 1273 picofarads would result in 90 degrees of phase shift. That could easily be enough to cause oscillation. In the peek inside the op-amp video, we saw how a constant current source in the emitter tail dramatically increased the op-amp's ability to reject common mode signals. But due to the inherent mismatches, there is a limit to how much can be rejected. Common mode levels change the offset voltage. We saw earlier how changes in the power supply voltage change the offset voltage too. The real mechanism at work here is delta offset voltage versus delta common mode voltage, and the delta offset voltage versus the power supply voltage for the power supply rejection. The reciprocal form of both are commonly used to give a positive number in dB. Since this represents the change in offset voltage, in order to determine the output voltage, the change in offset voltage must be multiplied by the closed-loop gain. Here's the common mode rejection for the OPA 222 series op-amp in decibels. This is the DC common mode rejection. The common mode rejection and power supply rejection are often plotted together over frequency since they share the same range. Note the rejection of the positive supply is different than the negative supply. This is because each supply affects the change in offset voltage due to a difference of bias point. The important part of this graph is to recognize that at higher frequencies, the rejection can go very low, like here for the positive supply, which is 0 dB at 160 kHz. Where you get in big trouble is trying to use switching power supplies, which typically have noise in this part of the spectrum. The op-amp will have little, if any, ability to reject that noise. Let's now look at power supply current. This is usually straightforward. The quiescent current is specified, which does not include the load current. It's usually specified as the current per amplifier, since the particular op-amp will be offered in a single, dual, or quad configuration. In the case of the TL084, it's a quad, so the quiescent supply current would be these numbers shown here times 4. The load current would need to be added to the quiescent current to get the total supply current. Calculation of the op-amp power dissipation is very straightforward. Here is an example circuit of a non-inverting amplifier with a gain of 4 and an input voltage of 2 volts DC. The output, of course, will be 8 volts. The output current is the sum of the current in the load resistor and the current in the feedback resistors. With the output of 8 volts, this yields an output current of 3.6 milliamps. The power dissipation of the op-amp is the total supply voltage times the quiescent current plus the voltage between the plus supply and the load times the output current. In this case, we have a total dissipation of 42.25 milliwatts. For AC signals, use the RMS value. If the input amplitude is indeterminate, use the worst case dissipation, which is the power supply voltage divided by 4, which follows the maximum power transfer theorem. Sometimes the op-amp spec will have a dissipation rating table. It will have a derating factor to apply above a certain ambient temperature. Here at 7.6 milliwatts per degree C at 60 degrees C. Let's say we are operating at 100 degrees C. 100 minus 60 times 7.6 milliwatts per degree equals 304 milliwatts derating. Subtract the 304 milliwatts from the 680 milliwatts and get 376 milliwatts, the maximum dissipation allowed at 100 degrees C. Because of nonlinearities and noise sources within the op-amp, the output is never pure. Total harmonic distortion plus noise is the ratio of all other frequency components to the fundamental and is usually specified as a percentage. It's specified this way because it's a simple measurement. You just filter out the fundamental and the power left is all the harmonics and noise. Here's a typical spec of 0.002% under specific test conditions. This concludes the Understanding Op-Amp Specification videos. There are some spec items I did not cover here that are broad enough in scope to dedicate an entire video on for each topic. One is op-amp noise, which we will not only go over the noise specifications of the op-amp, but do a full calculation of noise. We will also look at slew rate spec and make some measurements. There will be an entire video on stability and phase margin. Thanks for watching. Please click the like, subscribe, and notification bell so you don't miss any upcoming content.